Hello, welcome back to my channel, JBTeguihanon. Please subscribe for those of you who have not yet subscribed. Let us jump into our study today. This is again pressure, okay? From a mathematical perspective, we will take it from mathematical perspective. So, uh, we have already defined pressure from previous videos, and we have graphical presentation. It's very clear. And here we define it again that in any gases, liquids, it is common to call the effects of normal force acting on the area, we call it pressure. This is common. If delta force at an angle to an area delta A in figure 1-7 in here, this one, this is figure 1.7 normal components of a force. This is the surface area, and you have here delta A, specified location of the force acting on it. Okay, only the normal component, this guy here, enters into the definition of pressure, because pressure is liquid, pressure in gases, okay, is the effect of normal force acting on the area, and normal means perpendicular. This is your surface area, right? It is acting 90 degrees per force to this area here, and that is, and this area suppose is, this is your area, so your pressure P is equal to F over area. Okay, this force is acting on the surface normally, means at 90 degrees, not this way, not this way. Okay, if that is the case, then you have to get a component. Okay, so in here you have this case now. So there is a variation, there is an angle, and then he clearly defines that pressure is this guy here. The P is equal to delta N, this guy, over delta A, this guy here. Okay, limit delta A approaches 0. It is becoming smaller, your delta A. And then the unit of pressure is Pascal, PA, and that is 1 PA is 1 Newton per square meter. And we know that uh, Newton meter square is also equal to 1 kilogram times, so 1 kilogram per meter second square. Okay, so the corresponding English unit is pound force per square feet, or PSF, pound square feet. Although of course common, we have already have a video of this, is pound force per square inch or PSI. It could be PSF, it could be PSI, but most common of course is PSI. It is commonly used. Okay, uh, by considering the pressure, okay, acting on a triangular fluid elements of a constant depth, we can show that pressure at a point in a fluid at equilibrium, no motion is same as all direction. It is a scalar quantity. For gases and liquids in relative motion, the pressure may vary with direction at point. However, this variation is extremely small and can be ignored in most gases and liquids with low viscosity. Example, water. Water is low viscosity. So we have not assumed in the above discussion that pressure does not vary from point to point, only that a particular point it does not vary with direction. Okay, now let's have some pressure with variation in elevation. So suppose in figure 1.8 here, in the atmosphere, pressure varies with elevation. This variation can be expressed mathematically by considering the equilibrium of element of air in equation 1, in figure 1-8. Summing all the forces on the elements in a vertical direction, up is positive, gives us this. Okay? So here is the figure. Figure 1-8, forces acting on the element, acting on an element of air. So suppose you have here this element here. Okay, you have a force. It is elevated at Z. This is your ground. Z is equal to 0. Pressure here is 0. So this one is lifted up with Z. That's the height. So at the bottom, you have a pressure P, or you have the pressure force P times A. And that is actually pressure is equal to F over A. F is equal to P times A. Okay? And on top of it, you have also pressure P plus dP times A. And this is your A, right? And this guy here has a weight. The weight is this one. Density times G times area times dz. dz is like a thickness. Okay? So, according to our discussion here, summing up these forces, okay, you come up with this guy here. Summing all the forces on the elements in the vertical gives you this. dP, okay, is equal to negative density. This is density, and this is G, gravitational acceleration, U2. gravitational acceleration. That's constant. dz. dz is this guy here. Okay. So now if P, that is pressure, is a function of Z, the above equation can be integrated. So we can integrate this like this, right? P times Z minus P sub 0 is equal to negative. We integrate this from 0, from here is 0, from here is 0 to Z. Your Z is here. So you're actually summing up the value from this point here to that point there. You're integrating it, and what is inside the integral sign is this guy, density G dz. Okay, and that is this guy here. Okay, then for a liquid with a constant density, we write 1.8 using this guy. Then we have this. dP is equal to W, that is actually specific weight, times dH, where H is a measure positive downward. Integrating this equation, taking this as P is equal to 0, the result is this guy. Okay. This equation can be used to convert a pressure measure from water, mercury in Pascal. Okay. So this expression, this 1.11, is a formula that is very important. As I have said, if you have a reading on mercury, okay, you have a reading of pressure, mercury, right? If you have a reading H, and this is mercury, you can get the pressure, because this is have a value and that is constant. So in most thermodynamic relation, absolute pressure must be used. Absolute pressure is measured pressure or gauge pressure plus local atmospheric pressure. We have done this. We know this, right? P abs is equal to P gauge plus P ETM. ETM means atmospheric pressure. Okay? And we have here an example, or sorry, a diagram already, which we have also in the previous video, right? So for P abs, P absolute, okay, that is equal to this and this, right? Gauge is equal to 0. You have you have this P abs is equal to P atmospheric pressure minus P gauge. Okay, so same as before. Okay, so the negative gauge is called vacuum. So remember this, the negative gauge pressure is called vacuum. The gauge capable of reading negative pressures are vacuum gauge. Gauge pressure of negative 50 kPa would refer to as vacuum 50 kPa with signs omitted. Okay? So in figure 1.9, I've just discussed that. Shows the relationship between absolute and gauge pressure. So the word gauge, remember this, generally in statement gauge pressure or P, example 2 is equal to 200 kilopascal gauge. If gauge is not present, in general, it will be absolute pressure. So be very careful with that. Atmospheric pressure is in absolute pressure and will be taken as 100 kPa at sea level unless otherwise stated. It should be noted that atmospheric pressure is highly dependent on elevation. Okay? For example, here in Denver, Colorado, United States of America, it is about 80 kilopascal. And in the mountain city where elevation is 300 meter, it is 70 kilopascal. So as you go up from sea level, suppose this is your sea level, as you go up, pressure, as the elevation edge goes up, your pressure goes down, right? That is the relationship. Okay, so that's all for now. Thank you for watching. Please subscribe to my channel, JBTeguihanon, Engineering and Chemistry Tutorial. Bye for now. God bless.